Okay, so let me share the screen. Okay, so what we discussed last time was, let us quickly revise the mode 0, because from that mode 0 we are going to learn about other modes. So it is very much necessary to understand that thoroughly, right? So what was mode 0? In mode 0, that is, the name was interrupt on terminal count. That means as soon as you reach to your terminal count, as soon as you reach to your count, you will generate an interrupt by sending certain signal high or low. Okay, for that we have to write our control word. Control word, this indicates that particular counter is selected, and that counter is selected in which mode? In mode 0. So for that, and then what LSB, just to write LSB that was selected, that we have seen in the last lecture, right? What we have seen, that what this control word decide, this control word decide that which counter it is, which mode it is, then whether we want a count of 16-bit or 8-bit. So we know that in this, what is selected, counter 0 is selected, and just LSB is selected, then mode 0 is selected. Okay, according to that, in binary mode it is. So we have seen this, right? That is how this control word will decide, will configure your counter. As soon as your control word is returned, that your counter knows, that counter 0 knows that I am selected, now I have to work according to mode 0, right? That's why what will happen, this out signal which was high, it can be anything, it can be low or high, we are not sure about, but just to distinguish between these two, we are assuming that it was, if it is high, then it suddenly goes low. Why? Because it has to generate interrupt, it has to generate signal high when the count is rich. So it will be go low as soon as the count is, as soon as the control word is written. Very much useful. This will are these words, because this out behavior will be different for every mode, right? So this is very much useful words. That's why please focus on them. What I'm saying here is that as soon as control word is written, out goes low. Okay, this behavior is for mode 0, can be different for mode 1. Okay, fine. So now then LSB is written. That means it is, we are writing, we are putting our data on the lower data bus. That is what it is. It is value is 4. That will take one more cycle to reach, or to be written into counter's internal register, right? So these data lines are, as soon as we will write, it will be available to your 8254, but it will take one more clock cycle to be written into internal resistance of counter 0, right? What it will write, it will write it like the value is 4. So that 4 value is written here, and then after writing it, every negative clock cycle, every negative edge, not clock cycle, but every negative edge, it is going to decrement the count, because it is a down counter, right? And then as soon as the count is over, that means 4, 3, 2, 1, as soon as you will reach 1, or you will reach 0 rather, as soon as you will reach 0, it will make your out high. So this is what we have already discussed, right? What was this? This was like, if your gate signal is low, then your count is retained. This is also we have discussed. This was needed because I have to go from this in mode 1. This is the same one. What is that? Gate signal goes low, then the count is retained. Okay, your gate must be high to continue with the countdown. Now, if you are altering your LSB, like if you are altering your count, it of course it will take one more clock cycle to be written into, but it will get updated. So in mode 0, the count gets updated if you write intermediate, if you change your count intermediate. But of course, it will take one more clock cycle to reach to the end. So out, actually, after writing the count, mark the words, after writing the count, how many clock cycle, after how many clock cycle out will go high? After writing the count, suppose count is n. After writing the count n, after how many clock cycles the out will go high? Will it be n or n plus 1 or n minus 1 or n square? What it will be? After writing the count n, how many clock cycle will it take to go it high? Observe how many clock cycles. I'm writing it here. I've just written here. See, it is after writing means what? 8086 is writing, right? So if you are considering that writing in the clock register, writing in the counter register, then you might be right. But what is the point? After writing here, what it means? Who writes that? 8086 writes. Then it is internal operation of 8253, right? It is internal operation to 8253 to transfer the count from the data lines to counter register, right? Who will, if I'm writing, that means what I am putting this value 4 in my data lines, and my job is over is 8086, right? So I am writing on my data lines that now it is given to, at this point it is given to 82 what you can say 8253, it is already given. Now it is job of 8253. So how many clock cycle 8253 will take to make out high? It will take n plus 1. Why? Because already this is given. Job of 8086 is over here, right? So that's why it will be n plus 1. I hope everyone is comfortable with this. Everyone is getting this. Okay, so of course it is relative if you are starting, if you are considering from this, but no, we should not consider from this because our job gets over here. We are at 086, our job gets over here, right? Then it is handed over to 8253 and 54. It is job of 8253 now. Is it clear? So, so what we will say, it is n plus 1 cycles it will take. Okay, now let us go to mode 1. What is that? It is hardware triggered or programmable one shot. It is what here it will require to be triggered. That's why it is hardware triggered. You will have to use some hardware to trigger it, right? And that's why one shot is what that is. This type of signal is one shot, right? Like only one pulse is coming, then afterward it is low. Again one pulse will come, again it is low. So that's why you can say it is one shot event, right? So what is this mode? It is hardware trigger or programmable one shot. So what is the difference between this and the previous one? Here the gate signal is low. Okay, then gate signal is made high, or we can say it is made high for some time. That means using this gate signal, you are triggering your counter to start countdown. Sometimes we need that, right? We don't want that as soon as we load the count and it should start down counting. No, what we want, we have loaded the count. Now the trigger will take place, some event will take place, then it should get triggered, and then it should start countdown. That type of things are needed, right? So that is this mode 1. What it is, what we are doing here, this is control word 1, 2. This control word will decide that which counter it is. Okay, will the count will be LSB, MSB only, or LSB, MSB both, right? And suppose that counter 0 is selected, suppose that only LSB is selected, and which mode is selected? Mode will be 1, 0, 0, 1. Mode will be 1. Okay, so the mode 1 is selected, and then it is assumed that it is binary. Count is binary. So according to that, your control word will be ready. So as soon as you are writing your control word, your out becomes high. Whatever it was earlier, we are not sure about, but as soon as you are writing the control word, out goes high. This is different from the previous one. I hope you can recall and you can map these two things, right? This is the behavior, how it is designed to behave. We have to just understand that how exactly it behaves, right? So according to our requirement, we can, if we know this functionality, according to our requirement, we can use this 8253 and 54. We are not designing this behavior of out. We are accepting this behavior of out. We are learning that behavior of out, and we will use this behavior in some program according to our requirement. Okay, so we are not here to design the behavior of out. That means to design 8253 and 54. So what is our job in this topic? Just to understand how exactly it behaves and to learn how we can use in our application. Okay, fine. So here, as soon as the count is written, it goes high. Okay, and it will remain high till something, right? It will remain high. Okay, now what will happen? Now I am writing my count. I am writing my count, say 3. So what will happen if I am writing the count 3? Here I am writing. So what should ideally happen? After one clock cycle, that is on the next negative edge here, it should be written in my counter's internal register. Of course, it is not proper way to draw, but of course you can understand this. At this, after writing this, in one clock cycle, it must be written, and the next negative edge, actually it must be written in the counter, but it is not written here. See why it is not written? Because yet your gate was not triggered here. You have written this, right? You have written this, but at that time or after that even it was not written on the counter. Why? Because in that duration the gate was not high, right? Gate was low, or it was not triggered. Your mode 1 is that means it knows that I need a trigger here, right? So now if you will see, so now we are triggering using a gate. Now as soon as we are triggering our counter, what should happen? As soon as trigger happens, it will take one more clock cycle. It will take one more clock cycle. You can see here of you can see that this is that negative edge, this negative edge, you can see here that it will take one more clock cycle after the gate. It will take one more clock cycle to write the count on the counter. So after gate is triggered, you will take one more clock cycle, and it will write that count to internal count register, right? So here the count is written. At this moment the count is written. You can see the count is written. And as soon as the count is written, what will happen? The out will go low. Is it okay? Now what will happen? That it will start countdowning. It will start countdowning. And as soon as it will reach to 1, the out will go again high. Right? It will remain high till the next trigger. As soon as you are triggering once again, it will take one more clock cycle to write it in. One more clock cycle after this. At this negative edge, it will after gate, this negative edge, the count will be written. Okay, and then after again it will count down again. Whenever it will come to 1, after that it will come to 0 again. It will go high, and it will remain high till the next trigger comes. Okay, here your gate signal can be high, here your gate signal can be low. That depends. That is your choice, right? It just needs a trigger. Afterwards, if your gate goes low, that doesn't make any difference to this. Once it gets triggered, after that, what is the meaning of this dotted lines? Dotted line says that it can be high or it can be low. No issues here. Okay, but if it is if it is getting low, then also because it is already triggered in mode 1, it will not make any difference, or it will not create trouble. While here it was getting low, then it was creating trouble. It was latching the count, right? That will not happen here. Okay, now another case, if you will consider, here if you will see, suppose we are okay, here if you will see, before that out goes high, here ideally what should happen? The out should go high, because my 1 is reached. Now next count will be 0 0. But before my out goes high, my next trigger came. That means in this clock cycle the next count must be written, and that's why the next count is written, and the countdown is started, and when the count reached 0, the out went high. So actually this extension I got because of this trigger. Are you following? Because here ideally if it is this trigger was not there, then I should have out here high. Okay, but I got trigger before this goes high. That's why because of this gate signal my counter got updated. Okay, so what is the meaning? In mode 1 also, if you trigger before the previous counts complete, it will update the count. Okay, here what is that? What we are doing here is okay, here the count was written 2. Okay, the count is written 2. Okay, and after 1 clock cycle it will appear to your count register. So 2 1 0. Here what happened? Before this count complete, we have written another count. Okay, so so ideally what should happen? We have written this here. Ideally that should reflect here. Why it is not reflecting? What is the reason? This LSB is for updated before this count gets complete. What is the reason? Why it is not updated here? Yes, gate is not triggered. That gate is not given. So as soon as the gate will be given, then that count will be reflected. After, of course, one more cycle will be taken, and that count will get reflected in the out. Okay, now for how many clock cycles out remains low? After getting triggered, or after in the actual operation, right? See here if you will see in this case, when your operation starts, when your job gets over, your job gets over at this. As 8086, your job gets over at this. So after once you hand over your operation to 8254, it was taking n plus 1 pulses. Once you hand over your job to 8253, it was taking n plus 1 pulses to get your out high, right? Here, when your job gets over, when your when you trigger your gate, when you complete the operation of gate, then you are handing over the job to whom? To 8253. Once you trigger it, then it is job of 8253 or 54, whatever you consider in mode 1. So can you tell me in 8253 or 4 in mode 1, how many pulses the out goes low? For how many pulses? Yes, it will be n. It will be n. So you can see here it is n. So if the clock period is given to you, suppose the clock period is given to you, then you can easily find out for how much time the out will be low. That whatever the clock period into 3 or into n, whatever your count is, for that much time out will be low. Okay, so this is all about mode 1. Mode 2, what is mode 2? Let us go for mode 2. It is again very interesting. It is regenerator. You can see it is a rate generator or divide by n counter. So let us see what happens in this mode 2. In mode 2, gate is always high. So it is not triggered mode, right? It is high. So it is high, right? Fine. Now what will happen? Suppose you are writing this code 3 here. So of course it will take one more clock cycle to write that in the counter. Okay, so that is written internal register of counter. Here it is available at data bus. That is, it is available to 8254 or 3, but that will be transferred from the data lines to internal register. So that will take one more clock cycle. Okay, so this internal register will take 3, then 3, 2, and 1. So that is, suppose this is n pulses. Suppose this is n pulses, 3 is, so n is 3, so n pulses are there. So for n minus 1, it will remain high, out will remain high. And that last pulse, in the last pulse, it will go low. Okay. Then again, so that is fine. Now what will happen? Again, it will reload the count. I have not written that count here. I have not written the count. See, I have just given the count once. I have programmed my counter into mode 2. Right? Once I program into mode 2, then I will say, okay, generate the rate of 3 pulses. That means at every third pulse, you generate a pulse. That is the meaning. Okay. So actually this is generating a signal which is low for one pulse after every third, I mean at every third pulse is low. By every third, because LSB written 3, count is written 3. Okay, and for that every time gate must be high, so it is enabled one. So it is simply what it will do, whatever you count, you will have n minus 1 pulses will be high, n minus 1 clock pulses it will remain high, and then it will go for low for one pulse. Again n minus 1 pulse will remain high, again at 1 pulse it will go low. So actually you are generating a rate. What is the rate? That for that whatever the clock cycle, but every nth pulse will be low. Can you say like that? And the whole period will be n, but for n minus 1 it will remain low. Okay. So suppose I am having n is equal to say 10. So can you tell me and suppose clock period is 1 microsecond. Clock period is 1 microsecond. That means this clock, whatever we are having, this one clock cycle period is 1 microsecond. So for how much time out will remain low for every period? For how much time the out will remain low? Low. I am asking for how much time it will remain low. For how much time it remains low here? Observe. 1 watt. How much time it will remain low? For how much time it will remain high for every period? What is 2 and 1? What is, write the units here. 9 millisecond high, and okay, let us see what it says. 9 is a period. That means what will happen? This will be 9, 8, 7, 6, and then whenever it will come to 1, for 1 it will remain low. So let us see what will happen. It will remain high. It will remain high for when my count is 9, then my count is 8, my count is 7, my count is 6, 5, 4, 3, 2, and whenever it will become 1, at that time it is going to be low. Again, it will load the count 9, 8, 7, 6. So in that way, it will be high, and at last it will be low. I hope you can get that. Okay. So this is how it is going to behave. For n minus pulse, it will remain high. On nth pulse, that is only one pulse, it is going to be low. So can you tell me now the pulse will be low for how much time and high for how much time? This will take 1 clock period to decrement. This will take 1 clock period to decrement. So can you tell me 9 for high or low? Yes. And others? This will take 1 microsecond. This is microsecond. Na? This is microsecond. So Priyank, 9 microseconds for, yes, n minus 1 to 1, high to low. That is true. That is 8. Okay, what we are saying? Okay, we are writing this. So count, what I am considering is for n is equal to 9. Na? So this, whatever I have written, otherwise what I have to start with? 10. I have to start with 10. Okay. See, if n is, I'm sorry, I was wrong with the question. What is the case? See, if I am writing n is equal to 10, I have to start with 10. Okay. So in that case, yes, in that case, what will happen? For 9 microsecond, it will remain high, and for last microsecond, it will remain low. Okay. And again, it will start with 10, 9, 8, 7. I hope you are getting it. So 10 to 2, that many microseconds, it will remain high. And last microsecond, it will go for high. Sorry, it will go for low. Getting the point? And if the count is 9, then what will happen? If I wrote like count was 9, then what will happen? What will be the change here? Quickly tell me so that I can get idea that you are clear with. If the count is 9, then for how much time it will be high and low? 8 and 1. Prince, it is microsecond. Yes, you are correct with the numbers 8 and 1, but it is microsecond, right? Okay. Fine. So true. So that is how it will act. Why I'm taking, so see, can you see the pulse? It is not a square wave. It is not a symmetric one, right? If I'm writing 100 here, for the 99 times, it will remain high, and for 1, it is going to be low, right? While mode 3 is for the square wave generator. How it is different from this? It will generate a square wave like this, where most of the time, the high time and low time will be almost equal, right? This is how mode 2 and 3 are different. Right? So of course I will come to mode 3, but first I need to complete mode 4, then I will come to mode 3. This is remaining. Let us quickly see this. What is that? Suppose suddenly you were counting and gate goes low, then what will happen? Gate was required high here. Suppose it goes low, then the count is retained. Right? It will not alter the count. One interesting phenomena you will see here, very interesting one. See, what is that? Suppose gate is always high, but my count gets changed, right? So what it will do, it will first, so this is at 5, right? So what ideally should happen at this clock pulse, that 5 must be written somewhere here. What this is going to do is, whether it is a suitable one or not, other example you can also take. But in mode 2, what will happen? Suppose you are changing the LSB, it will complete the current count first. Suppose you are having, say, 10 here, right? So it is here 10, then 9, then 8, and 7, right? And somewhere here, the count changed, right? So what will happen? Ideally, what we expect here, it will start writing 5 here, but it will not happen. It will first complete 6, 5, 4, 3, 2, 1. It will complete this count first, and then it will load this. So it will complete its countdowning for the loaded count. It will make that pulse low for that current count. Then again, it will not reload. Here, what was happening? I completed the count and I again reloaded which one? Which one I reloaded? The same one, because the alternate was not written, right? But here what it will do, if you are changing it, it will reload it. But once it will complete the current count, then it will reload the new count. Is it okay? So this is what the interesting behavior of mode 2. Of course, it has to reload, but it will check the count once it completes its task of current countdown. Right? Before reloading, of course, you will see here, when it is completed, then it will reload the new count. Okay. Now, next, if you will go for software triggered stop, that is, this is mode 4. It is similar to mode 2. What we are doing here is just a difference. What is the difference that we have to understand? If it is similar, we will not have a. It is not same, right? What is what is the similarity and what is the differences that we need to understand? First difference is that it goes low for 0. That means it remains low for n pulses, not n minus 1 pulses. It remains high for n pulses and it goes low on the 0th pulse. It is for, if I'm writing count 3, that for n count it will remain high and then after it will go low for 1. Okay, and what is the next one? So what we are saying? So gate 1 will be needed. It will remain high for how much time? N into t duration. What is t? T is a clock period. What is n? That is a count written. So it will remain high for how much duration? N duration. Okay. And what is another difference? That it is not reloading the count. Observe. It gets completed. In mode 2, what was happening? The count was reloaded here. The count. So sometimes we need this operation, but we don't need that count should be reloaded. We don't want to generate it repeatedly. Then we can use this mode. What is that? For n pulses, it will, after n pulse, it should give you low. If you want that type of applications, then you can go for this. And if you want to generate it again and again, you have to reload the count again and again. It will not continuously do that operation. It is not periodic. Okay, so these are the two differences between mode 4 and mode 2. Okay, now what happens? Suppose I have reloaded the count. If I have reloaded the count, and I've loaded the count, not reloaded. I've loaded the count, but my gate is low. Then what will happen? As soon as my gate will be high, then operation will start. Okay, so of course we need gate high for this. Okay, so as soon as your gate will be high, after that your operation will start. And what will happen here? Suppose you are altering your count in between, yet your pulse was not low, right? So it will not complete the count as mode 2 was completing it first, right? It will alter the count. See here, ideally what should happen here? It should go low. But if the previous one is retained, but no, because the new count was mentioned, according to new count, the counter was loaded. Now according to new count, whenever the out should become 0, it will become 0. So that is the difference between mode 2 and 4. What are the differences? I will repeat them again. First is it will not reload itself. Second one is that after n pulses, on the 0th pulse, it will go low. Not like n minus 1 pulses, nth pulse, it will go low. And third is, if you are changing the LSB in between, if you are changing the count in between, it will get changed. Not like it will get completed first, the previous count will complete it first and then reloaded. So these are the three basic differences between mode 4 and mode 2. Any doubt up to this mode 2, mode 4, mode 1 and 0? We have completed 0, 1, 2, 4. Any doubt up to this? Okay, so I'm assuming these things are clear to you. That's great. Now we are going for mode 5, which is a combination of mode 2, 4 and 1. This is hardware triggered stop. Right? Hardware triggered, what you've seen somewhere earlier even. What was that? Where was that? Here, hardware triggered. That was mode 1. What was happening here? You were triggering using gate. That is what the difference was, right? So that is going to happen here. Hardware trigger. And what is stop? Stop we have seen somewhere here. Stop is what? This type of pulse is known as stop. So it is high and suddenly it goes low. This is called as stop. Again, it is high, it will go low. This is stop. Okay. this strobe is repeated here in this. That's why it is rate generator. When the strobe is repeated, you are generating a strobe at certain rate. That's why it is known as rate generator. Otherwise, it is also strobe generator, but it is not just strobe is periodic. That's why it is better to call it a signal with some frequency. That's why just different names are given. You should understand the operation by the name itself, right? So here, can you understand what is happening? You must have, you must be generating a strobe, kind of this kind of signal. You must be generating this kind of signal when you are getting triggered. That is the meaning. Okay, so it is simply mode 4 with the trigger. What was mode 4? That as soon as the count is written, it will go high for n pulses. On the 0th pulse, it will go low, right? And it will not repeat itself. So this is mode 4, right? But this operation will take place not as soon as you write the code, but as soon as you trigger it. So once this is triggered mode 4 kind of thing, right? So as soon as you will trigger, as soon as you trigger, the code is loaded, right? And then code will, it for n pulses, it will remain high. And for then next pulse, it will go for low. So this is what mode 5 is. So see, this is, so if what kind of application it can have? See, if I want to reload the count in mode 4, right? If I want to reload the count in mode 4, what I have to do? I have to provide, I have to write this operation. I have to write this LSP, right? But if I want to reload the count here, what I need to do? Do I need to write it again? No. What I need to provide? Just a trigger. If I will provide a trigger, then it will, yes. So that is how it is different. What was in mode 2? In mode 2, if the gate is high, it will automatically will restart the countdowning with the same count. If you want to restart the countdowning with the same count or different count, in mode 4 you have to write the count again. In mode 5, if you want to restart, you have to just trigger your gate. Again, that can have different applications. In the different scenario, you may need different operations. Okay, so these are the differences of mode 3, 4, and 5. Sorry, 2, 4, and 5. Okay, so here you can see, suppose I have written, I have triggered the gate. According to that, the countdown started. But in between, again, the gate was triggered. So in the next clock cycle, again, the count is reloaded, though the previous one was not completed. So if you are triggering before, then definitely it will be restarted. Only in mode 2, it will complete the previous one. Otherwise, as soon as you are updating it, the counter will get updated. Okay. In this, if you will see, what is that? You are writing earlier the count was 3. Now you are having count 5. Okay. Then you are writing the count 5, but you are not triggering it. That's why that count will not be written. The previous count operation will get over, right? And in the next trigger, the previous count, whatever the count written, will be loaded. So after triggering, the count will be loaded. Whether you are changing, you are making it 5, 10, 15, doesn't make any difference. Once you are triggering at the time, whatever the count is written, that count will be loaded and countdowning will start. Okay, so this is all about mode 5. Now we need to learn just only one mode is remaining, that is mode 3. And very important mode it is. It is a square wave generator, most commonly used one. Okay, so what we will do here, see, this is a control word for selecting counter, selecting mode, and read-write operation in LSB or MSB or both. So according to that, we are writing the LSB. Say I should go for 4 first. I will come to this. Let me start with 4 first. I'm writing the count 4. Okay. Gate is always needed high. The gate is needed high. Okay. Once you write it, it will take one more cycle to load it into the counter. Once it is loaded into counter, what will happen? It will not decrement by 1, it will decrement by 2. Okay, so it is keeping your out high, and it is decrement by 2. So it will decrement the count by 2. Okay, so 4 will become 2 now. Okay, Then again it will, so because it is not 0, what will happen? It will again decrement the count by 2 and it will keep it high, right? Now what will happen? Now again it will decrement it by 2. So what will happen? So it will become 0 now. Okay, so if it is becoming 0, then it will say, okay, now I have to reload the count. So count is reloaded and it will make your out 0 for that count. Okay, new count, it will make your out 0 for that count, and uh, it I mean it will make out 0 for the new count, because it will alter the polarity of out. Okay, again it will decrement it by 2. So now again it is so continue with the previous polarity of out. Now the count is 0, so alter the polarity of out and reload the count. What is the count? It is 4. So keep it for and decrement it by 2. Is it 0? No. Then keep it high. Right? So in short, what we are doing here, that for 2 pulses we are keeping it high, and for 2 pulses we are making it low. Why for 2 pulses? Because the count was 4 and we are decrementing it by 2. Or rather I should say, for whatever the pulse I have written n, for n by 2 pulses I am keeping it high, and for n by 2 pulses, n by 2 clock pulses I am keeping it low. So that's why if you will see, after this time it is a square wave. What is the period of the square wave? Suppose my clock period is 1 microsecond. What is the period of the square wave? Count is 4. Clock period is 1 microsecond. What is the period of my square wave? Yes, period is 4. The period is 4. Why the period is 4? Period considers low and high, both of them. This is the period, right? This is the period. 4 will be the period. 4 microsecond, 4 clock cycles will be the period, right? And for how much time it will be high, and for how much time it will be low? For 2 and 2, provided, what is you assumed here? The count is 4. That is what your assumption for 2 and 2. Yes, 2 microsecond high, 2 microsecond low. Assume that count is 5. Then suppose the count is not 4 and count is 5. Then what will you do? What will be the period first of all? Yes, it will be 3 and 2, not 3 and 3. Janil, we cannot go for 6 microseconds, right? We have to manage our period to 5 microseconds. So whatever the count you have written, according to that, this period of a square wave will be that many clock cycle only, right? Suppose I am writing count 5, that means the period of my square wave must be 5 microseconds. Okay, so as Kushal suggested, that will be true. What it will be? You have to go for uneven positive and negative cycles, right? They will not be equal. So your positive cycle will be little larger than your negative clock cycle. You can see that here. You cannot increase the size, right? You have to go for only 5 counts. So this is written. Then for after this, I hope you are getting it. I'm not good at drawing this, but okay. So this is what is written here. Okay. Now if you will see 4, 3, 2. So for 3 pulses it was high because count was 5, and for 2 pulses it was low. Again for 3 pulses it was high, and 2 pulses it was low. So here your period of your square wave will be 5 clock cycles. Okay. On period will be 3 microsecond. Off period will be 2 microsecond. Why we are assuming that 1 clock cycle is. See, this is for understanding purpose. Here you can go with, you can write it like 5, 3, 5, 3, and 1, and then it will go to 0, right? So actually they have started with the even number that comes after, which is below this, so that you can manage this one. That's why. So that you can manage this one. Okay. But again, it is just for understanding purpose, right? So what they are doing here, they are taking the even count here. So at least this will be managed, right? And here we have to go up to 0. So that you can go. This will be easily managed. And for this, you have to just go for 0. So keep for 0. Even it is 0, then keep it high for that. And whenever it is low, then count goes 0. Then keep it. Make your out high. If your current out is low, and if your count goes to 0, make your out high. And if your out is high, if your count goes 0, keep it high for that even. Kind of thing is implemented. That's why. Okay. So, what will be the output? Output will not have this number. Output will not have this number. Output will have this wave only. In output, you will have high for 3 microsecond if 1 microsecond is a clock period, and it will have low. You will not see the count anywhere. The behavior, whatever the output is this pin only. Okay. So in whatever way you want to understand, that's okay. But what they want, how it is implemented, that is shown to you. Okay. Now, so this is for so that is what we have skipped last time. I told you that I will come to this point once again. What was that? Here you will understand it now easily. This one. Suppose the clock is this frequency, then period will be what? This will be the period. How we will get period from the clock frequency? 1 divided by frequency. 1 by f is equal to period. Now n is loaded, then how much time it will be in mode 3? What will happen? Suppose in mode 3, for how much time it will be high? It will be n by 2 into this period, it will be high. Okay, and for the same time it will be low if n is even. High and low will be of this duration. But if n is odd, then what will happen? N plus 1 by 2, it will be high, and n minus 1 by 2, it will be low. That you can see, 5 plus 1 by 2, that is 3, and 5 minus 1 by 2, that is 2 periods, it was low. Okay, so so what if n is odd? What will happen? High portion of the output will be slightly wider than the low portion. Okay, that is all about mode 3. Okay, now we are going for the read operations. Okay, this is remaining. One more waveform is remaining. What it says, if your gate suddenly goes low, what will happen? The count is retained. As soon as it will be high, it will continue its operation. So gate must be high. If it suddenly goes low, the operation will halt. Okay, so that is all about all the modes, 0 to 5. That is 6 modes we have completed. Any doubt in this? Okay, now we are going for the read operations in 8254. So what is read operation first of all? So we are having the count. We want to read the count in between. We want to see that how exactly my counter has reached. What is the value of the count, right? So if I want to go for that, I have 3 options. What I will do, I know that what is my counter register. Suppose I know my counter 0 has address 94, counter 1 has 95H, 96H, and 97H. So we will have these addresses. We have seen that example last time, how to allocate the address, that we have seen like this, right? We will give it the chief select, and this A0, A1 will select the address of counter 0, counter 1, counter 2. So simply what I can do is, suppose this is the address, I can use in 94 in AL 94, or in AX, whatever the count is, you will take it at 94, right? You can write it like this. So what will it will do? Whatever is in 94, 94 is counter 0. Suppose it is counter 0, it is address of counter 0. Then 94 is whatever the count of 94 is loaded in AX. Okay, but you know that it is 16. It is possible that while you are loading it here, while you are taking the value from your counter to your uh, uh, in your AX, in operation will take certain clock cycles, right? This operation will take certain clock cycles, right? Can you take how many bits you can read from in? Can you read a 16 bit in the in instruction? Can you read 16 bit in instruction? Can you read 16 bit directly? You cannot read 16 bit. Why you cannot read 16 bit here? Because your data line of 8253 is how long it is? How many data lines in your 8253 you are having? Just 8 data lines, right? So even though that is permitted by my processor, then what will happen? But I have to take the count. Though I want to read 16 bit, I have to read it as in 2 clock cycle in the operation of two 8-bit readings. Why? Because data lines of my 8254, which is going to provide me the count, is just 8-bit wide. So if I want to read 16, I need to have 2 clock cycles there, right? So it is possible that because the counter is running in between, so whenever you are reading this one, at that time your count is say FFFF, right? Whenever you are reading this, at that time your counter is FFFF, so you will read this by in instruction FF is written, FF is read. Then in the next clock cycle, what you are expecting, next FF. But while you are doing this reading operation, at the same time counter is on. So in the next clock cycle, what will be this count? It will be 00 F00. It is decrementing, or what it will be. Again, I have taken wrong example. What I am expecting here, I have taken wrong example. Let me take a better one. But I hope you understood. You got the essence what I want to say here. Suppose my count is 0000 and I want to read this, right? So in first 8 bits, I'm going to read this 00. In the next clock cycle, I am expecting this 00. But when I'm reading this, the clock is on, the countdown is on. So what will happen to this countdown? It will become FF, that you know. FFFF it will become. So when I'm reading the last, it will be, when I read this, it was 00. But when I will read this, at that time, this has become FF. So what the count I have read? That was FF00. Getting the point? So whenever I'm having, I can use the simple read operation, I can use this type of instruction, I can use this in twice, but at that time, what I have to do, I have to stop my counter. How to stop your counter? How can you stop your counter? Yes, by keeping your gate low. Yes, by altering your gate. True. Yes, you can change your gate value. So that is one way. Simple read operation, just make your counter stop. But sometimes we don't prefer it. Because I want to read, I will stop my counter. That should not happen. No? I want that my counter should continue its operation, but still I want to read. But I cannot read because the problem is that I am not storing my count. That is a problem. No? That count is not stored. That's why I have to stop and I have to read. But what if it is already counting the time? I want to read it between, but if I will waste the time, the operation of the counter will go wrong. It will not be accurate in the timing. Right? So what should we do? The problem is that I am not latching the count. So now the next option that I have is that if you want to read, latch the count. If you want to read it, don't stop your counter. Latch the count. Store the count. Okay. And that is what the next option you have. That on the fly. What is the meaning of that? Without affecting your counting process, you are going to read it. Okay, so this is also known as on the fly. Okay, so now how to do that? So for that we have one operation. If you remember the your control word, what was your control word? Here. What was this 00? This RL1 and RL0 was 00 for latching the operation. Right? So this we have never used. What this will do, whichever counter is specified by this 2-bit will be latched. The value of that will be stored in some internal temporary register. That is the meaning, right? And that value, that is what the next option that you have. Let us see. So that is what the counter latch command, what to do? Select the counter that you want to latch. Which counter that you want to latch, that 0, 1 or 2. Okay. And what is next? This must be 00. Why? This is RL0 and RL1. The 00 will indicate that you have to latch, and this will be don't care. This we are not worried about, that which mode it is or whether it is binary or decimal count. We are not interested in that. So let us keep them 0. Okay. So this is, if I am keeping all this 0, this will indicate counter 0. This will indicate latched operation. That means counter 0 is latched. Okay. And what is this? These are the don't cares. That's why they are taken as 0. So what we have taken in my DX, I have taken the address of my control word. That is, it was 97 here. Here, if you remember, it was 97. So that 97 is taken in DX, or if it is 16-bit, it is taken in DX. Then the control word value is written, which says that latch counter 0, that is given to that control word. And then whatever the whatever the counter 0, if I will write the address of counter 0, that is 94 here, that value of that 94 address will be so 94 I am storing in the address of counter 0 I am loading in dx. So assuming that it was 16-bit, that's why we need dx. Otherwise, or you can directly write your address here in the in instruction. But assume it is 16-bit, counter 0 address is 16-bit, that is stored here, not move actually. This is immediate data. In that way, you can say, right? You can assume that this instruction is like move dx 94, or rather if it is 16-bit, we are considering that 0094, right? So this value is stored in dx, and that counter 0 address, if you are reading it now, what it will provide you, the latch value of the count. So now it is not problematic. Why? Because what we have already instructed in using your control word, that please latch this value. Okay, and the next option that we are having is read back command. If you will see here in the control word, so what we have completed in this control word? Okay, so in this control word, we completed all these 4, but we have not discussed about this 1 1. This 1 1 is, which value is let? That whatever the current count is, that is let. Like 5. Suppose I am. Let me show you that. Suppose I am somewhere here, right? So my counter is 4 3 somewhere. Suppose here I am informing my counter, or if I 8254, that lets the word. So what it will store? It will store 2. So this will be stored, and then if I'm writing in AL and the counter 0 address, then in AL 2 will come. So it will continue its operation, it will not stop, but this 2 value will come in AL. Is it solving your doubt, Priyank? Should I explain again? Is it clear to you, Priyank? Yes or no? What happened? We add the new count value. So see, whenever you are giving the latch command at that time, whatever the count is, that will be, see, latch is what? Like there is a register, right? So whenever we are saying latch it, at that time, whatever the count register value is, that is stored in that register. That's it. Okay. Then you are altering it, you are modifying it. That will not be stored. What you will read a register given in that what is latch, the current value of the count register is latch. After that, current register count register can get updated, and it will not affect that register value, temporary register value, which we are reading. Is it making sense now? Okay, so I think we will not be able to complete the next one. That we will take after sessional, that read back command. Okay, I'm going to put this PPT, and some problems are given here, right? Let us quickly see what we will not solve this, right? But of course, I can give you the hint so that you can solve them easily. What you have to do? What is the port address in this figure that you have to find out? That means you have to see that what is the port address of counter 0, counter 1, 2, and control word. How will you find out? You know that you have to see from A15 and A0. So what should be the value of A0 to A15 in this figure so that counter 0 will get selected? That you have to see. This is 8254. So here A15 is there somewhere, and here you can see A0 and A1 from 8086 is given, and that A14 to A2 are not given to you. That means they are don't care. So you can keep any value of them. For simplicity, you can keep them 0. This must be 1 so that this will get negated, and that this will become 0, and this chip will be selected. Okay, so A15 is compulsorily 1, A14 to A2 are 0, right? And A0 and A1 are can be different, 0 0 0 1. According to that, this counters will get selected. So of course that you have to solve this, right? What is the next question? that generate 1 kilohertz square wave from counter 1, right? And clock cycle is given 2 megahertz, right? So first of all, you have to decide what should be your count. What should be your count? If you want to generate the period of 1 kilohertz, that means 1 kilo pulses, 1000 pulses in 1 second you must have. You must have 1000 pulses and your clock cycle is 2 megahertz. What should be your count? Okay, let us see that here. That is again required. Let us see that here. Um, in how many clock periods I had one pulse, one period I had? In how many clock pulses I had one period? So it was 1, 2, 3, 4, 5, 6. Not 6. Okay, it was 5. Okay, it was 5. True. Why it was 5? Because whatever here, what it will be, if you will see here how many it will be, totally was 4 periods, right? 4 clock pulses was for the period, right? That is n clock pulses were required. N clock pulses were required for a period, right? So if for one period, if in n clock pulses, if one period comes, right, then how many periods you need? Like okay, sorry, one period comes in n clock pulses, right? So how 1000 clock pulses, 1000 pulses will be how many clock cycles will be required for that many pulses? So it will be what it will be, 1000 into n. I hope you are following. So what it is? So what we are having here, see, if whatever my clock period is, whatever I am having, my clock frequency, whatever my clock frequency is, clock frequency divided by my count will give me the frequency of my signal. That we can see in, suppose this is period of 1 second. How many clock pulses I am having? I am having 5 clock pulses here. No, we cannot take it. We have to complete it. We will take more time, but we will complete this, right? Okay, what I am saying here, if you are not clear, I can repeat. We will take 2-3 minutes more, no issues. Even we will take one more extra lecture if needed, but we are going to complete this now. Okay, so what I am telling you is, forget about this. Let us have one equation, and from that equation you will understand it better. What is that? Clock frequency divided by count is your signal frequency. What is frequency? The number of pulses in 1 second. Okay, this is my signal frequency. Assume that this is 1 second, right? This is 1 second. Okay, in 1 second, how many pulses I am having? 5 pulses of clock. That means my clock frequency is 5 hertz. Can I say like that? Assume this is 1 second. In 1 second, I am having 5 pulses, 1, 2, 3, 4, and 5. I am having 5 pulses. That means my clock frequency is 5 hertz. What is my count? Count is also 5. That means what will be my signal frequency? That will be 1. That is, this was, so that, what is the meaning of that? In 1 second, I must have 1 pulses. And if you will see that this is 1 second period, in that I am having just 1 pulse. Okay, so this is the equation that will help you. Now in this, if you are using that equation here, what is this? What is my, I want to generate the signal frequency of 1 kilohertz, that is 1000 pulses in a second. What is, how many pulses in a second I am having for the clock? 2002 into 10⁶ pulses in a second I am having in a clock. So what should be my count such that this will happen true? So in that way you can find out your count, and that count will be 2000. If it is 2000, if you are dividing it with 2000, it will become 1000, right? So suppose I am writing a count of 2000, so what will happen? For 1000 counts it will remain low, and for 1000 counts it will remain high. Okay, so are you clear with this, or we need to go for one extra session for this? Should you 10 to 15 minute session will be needed if you are not clear with this? Do you need 15-minute session? We can go with that. Okay, what example is not clear? Is it the what about feedback from other? Otherwise I can explain this individually even. What is the station? Should I take 15 minutes? Give me the time quickly. In the lunch break? Will it be fine for the lunch break? Okay, let us take with the example. Okay, let me explain you the example. Let me show you that. Just a second. If only example is not clear, then let us see. Okay. Clock period is 2000 megahertz. What is the meaning of that? 2 megahertz, that is 2 into 10 raised to 6 clock pulses will come. So if I'm using this equation, what is that equation? Equation says that whatever your clock frequency is, thank you. Okay. Okay, fine. So, okay, what was the example? What it says that whatever my clock frequency divided by count will give me my signal frequency, right? Now here what is given to me? Something is given to me is clock frequency is given to me and the signal frequency is given to me, and the question is what should be my count, right? So first of all, what is the question? Let us read the question. Write the instruction to generate 1 kilowatt square wave from counter 1, right? And assume the gate of the counter 1 is tied to 5 kilowatts through this resistor, 5 volts through this resistor. That means your gate is always high. That is the meaning. So you can simply ignore this line. What it says, your gate is always high. So no need to worry about this. Gate is always high. Now, what you have to do, you have to generate 1 kilohertz pulse to counter 1, right? So first of all, you have to generate your control word. What your control word will say? The control word will say that which counter, so counter 1, okay, which, then you have to write that whether you will write just LSB or just MSB or LSB first and MSB later, that you have to write here. After that, you have to decide which mode. Because you have to generate a square wave, that's why it will be mode 3. And then you have to write whether the count will be written in BCD or binary. Okay, assume that it is written in binary for now. Okay, now only thing is that you have to decide whether you will go for LSB or only MSB or LSB, MSB both. For that, you need to know what will be your count that you want your counter to have. Okay, so that n value is needed, and that n value will be obtained by this equation. What is that? Equation is clock frequency divided by n is equal to your signal frequency. Okay, clock frequency is given 2 megahertz. Count, I don't know, and this is 1 kilohertz. So what will be n value? N value will be 2 megahertz divided by 1 kilohertz, and that is what is 2000. N value is 2000. Okay, fine. So yes, it will be 2000. Now let us write this program. How will we write this program? So first of all, we have to write this, say 2000. Can I write this 2000 in 8 bits? Can we write 8 in 8 bits? Can we write 2000? No. So we need 16 bit. That's why this should be 11. First LSB, then MSB. Okay. What is so now? Now let us see how we are doing this. Counter 1 has address 8001. Counter control word has address 8003. Assume that this is given to you. Otherwise, from the figure you can understand. These are the addresses of counter 1 and control word. Okay. Now I am taking this control word. I am storing it to the address of control word. So this control word is written in that I have programmed in mode 3 counter 1, and the count I have not mentioned, but I have mentioned that it will be 16-bit count. Okay, now find out a decimal equivalent of this. Find out decimal binary equivalent of this. What is binary equivalent of this? It will be 07D0, whatever, if you can check it later. 07D0 is a binary equivalent of 2000, and that I have to write. So first I have to write this D0 in control word, and then I have to write 07 in this control word. So by writing this count, what I'm mentioning that my count is 2000 here. That means for 1000 pulse, it will be high, and for 1000 pulse, it will be 1000 clock pulse, it will be high. For the next 1000 clock pulse, it will be low, right? I am repeating here for the understanding purpose. What will happen here? So assume that this is my square wave and this is my clock pulse. This is my clock pulse. For how many clock pulse my pulse will remain high? For how many clock pulse my out will remain high? My count is 2000. Yes, for half. So it will be 1000. For 1000 clock pulses, it will remain high. And for 1000 clock pulses, it will remain low. Can you tell me in 1 second how many clock pulses I am having? In how many clock pulses I am having? Is it 2000? Is it 2000? 2 megahertz. Is it 2000? Okay, in 1 second, how many clock pulses I am having? In the period is 2 megahertz. Are you getting? The period is 2 megahertz. What is the meaning of that? Clock will have 2000 mega pulses in a second. Are you getting the point? So in 1 second, I am how many pulses I am having? I am having such 2 mega pulses of clock in 1 second. That is what my clock frequency is. So it is having 2 mega pulses in a second. Okay. And what about my actual square wave? How many pulses I will have in my actual square wave? Because I know that for the 1000 pulses out of this, it will remain high. And for the next 1000 pulses, it will remain low. That is, I will have 1 clock pulse for the 2000 pulses of my clock. I will have 1 clock pulse in the out, 1 pulse in the out for 2000 pulses in a clock. Why? Because 1000 pulses of clock this will be high, and for the next 1000 pulses, it will be low. So I will use 2000 clock pulses to make 1 pulse in the out. So can you tell me if I am having 2 mega pulses of clock in a second, how many pulses will I have here in this scenario, in this cycle? I mean, in this 1 second, it will be 1000. How you reach there? Have you reached there? So you took, okay, because 2 mega pulses I am having in a second, right? And I am using 2000 pulses for creating 1 pulse. So this many pulses I must have. And that is what this equation is. That is what this equation is. That clock frequency divided by your count is your signal frequency. Is it clear to you now, everyone? Yes or no? Are you clear with this example now, no? Everyone? Priyank and others? Okay, great. So now we are stopping our discussion here. Only thing remaining is the readback command. We will start with readback command in the next session.